So in the previous class we have discussed steady state operations. Let us recall the overall response of the system. The overall response of the system C of t will be having steady state response as well as transient response. So transient response plus steady state response. So in the previous sessions we have seen what is the steady state operations for different systems. We have done analysis and we have derived the expression for static error coefficients like positional error coefficient, velocity error coefficient and acceleration error coefficient. Along with we have derived what is the steady state error for different types of inputs. So in this session we will be starting what is a transient response. Transient response is the response of the system where the controlled output variable will be varying with respect to time. That means at the initial stages the amplitude will be high. After that the amplitude will be reduced because of damping, and then after that you will get a stable input. So this part where the amplitude will be varying with respect to time is nothing but it is a transient part. And the next stage where the input will be maintaining in a stable fashion, that is called as steady state part. So this part is nothing but it is a transient part. The transient part, there are different things in transient part. We will be calculating what is the response of the system, what is the controlled variable with respect to time. So let us start the analysis of transient response. Here we will be doing analysis of transient response for first order system as second order system. So let us see what is the transient response of first order system. Again, in the previous sessions we have discussed what is the order of the system, what is the type of the system. Order of the system is nothing but it is the total power of S in the open loop transfer function. The type of the system is number of poles at origin, that is nothing but it is a type of the system. Let us recall a simple basic first order system. The first order system is having a transfer function like this. This is a g of s transfer function in the forward path, and this is a reference input signal, we will call it as R of s, then controlled output signal with a unity feedback. This is first order system. You can have an electrical circuit also. So representation is very easy if we use a block diagram. That's why I will be using directly the block diagram analysis. So G of s is nothing but it is 1 by Ts, H of s is 1. So this means the first order system with unity feedback. This is the consideration what we have taken. 1 by Ts is common whenever we take up a first order system. This is a block and this block is having a feedback of unity gain. So generally we will consider negative feedback for the analysis. Let us take the overall transfer function. The objective of obtaining transient response is, here we are seeing controlled variable variation with respect to time. What is controlled variable? Controlled variable is nothing but it is C of t. And C of t we have to write. What is a C of t? The expression will be in terms of t. Why? Because it is varies with respect to time. So we need to obtain C of t. How to obtain C of t? To obtain C of t, first we need what is the closed loop transfer function. So this is in terms of S. After that if we make L inverse we will get t. Let us obtain what is a closed loop transfer function for the system. What is a closed loop transfer function for the system? C of S divided by R of S will be equal to these two blocks. So those two are in opposite direction, and this is a minor feedback loop. If you eliminate the minor feedback loop, what you will get is 1 divided by 1 plus st. So this is the overall transfer function for the first order system. So 1 by st, this is g of s divided by 1 plus 1 by st. So if you simplify this, you will get this expression. So 1 by st is the expression for closed loop transfer function, and we want only c of s. I will send r of s to that side. So what happens? R of s divided by 1 plus st. So this is the response of the system in terms of s. This response of the system, response of the controlled output variable, is proportional to the reference input signal. What is that signal? So R of s will have different varieties. It can be a step input, it can be a ramp input, it can be an impulse input. So let us take each input into considerations. First, I will consider unit step input. Again, recalling, what is the reference input signal for unit step input? It is R of t will be equal to A. If A is equal to 1, it is unit step input. For unit step input, the value of A is equal to 1. So R of t will be equal to 1. If you apply Laplace transformation, you will get R of s. What is R of s? R of s is 1 by s. What we require? We need R of s here. So I will take the same expression. Therefore, what is my controlled output variable? Controlled output variable C of s will be equal to, what is R of s here? 1 by s. So directly I will write 1 divided by s into 1 plus st. So this is the controlled output variable for unit step input. How to simplify this? Again, this simplification is done based on partial fraction method. So I will take a by s plus b divided by 1 plus st. So they are linear powers, directly the substitution. If I take LCM, 1 divided by s into 1 plus st is equal to, LCM term is s into 1 plus st. So this term I will keep here, s will get cancels. I will get a into 1 plus st plus here 1 plus st will cancel because denominator I will keep here. I will be remaining with only s term, bs. So this term will get cancels. 1 is equal to a into 1 plus st plus bs. So engineering part is only this. You have to simplify. This is the basic method of partial fraction. I will take 1 plus st is equal to 0. So s will be equal to minus 1 by t. I will be substituting s as minus 1 by t in this equation. It will be 1 is equal to a into, if you substitute s is equal to minus 1 by t, this term will be 0 plus b into minus 1 by t. So minus 1 by t goes here. The value of b will be minus t. Then again put s is equal to 0. This term, if I put s is equal to 0, then 1 is equal to a. This term will be 0. So I will get a is equal to 1. Again I will put the values of a and b in this equation. Therefore 1 divided by 1 plus st, s into 1 plus st will be equal to a. What is the value of a? A is 1 by s minus b is t divided by 1 plus st. So this is a term. So again I will replace, therefore C of s will be equal to 1 by s minus t divided by 1 plus st. So this I will call it as A. I will be substituting the values of this term in A. So this is what I will get, the C of s value. This is not an important here. I want C of t. How to get C of t? I will be applying Laplace inverse. Let us recall some of the rules in Laplace transformation. So the Laplace transformation, first rule is the Laplace of 1 is 1 by s. Second one is the Laplace of e to the power of at. Whenever a is positive, you will get minus a, 1 divided by s minus a. Number 3, Laplace of e to the power of minus at, 1 divided by s plus a. So again I will add these formulas. If I require, I will be using this. First, let us recall only these three formulas. Whenever I take Laplace inverse, so Laplace inverse of 1 by s is 1. So this is in terms of t, this is in terms of s. If I take Laplace inverse of 1 by s minus a, it will be e to the power of at. Similarly, apply Laplace inverse here, C of s changes to C of t, and what is the Laplace inverse of 1 by s? It is 1. So 1 minus, what is the transformation here? So here what we can do is we can simplify this part. How to simplify this? So I will be simplifying this further. 1 by s minus, I will take t common in the denominator. If I take t common in the denominator, so st plus 1, t common, so s plus 1 by t. This is what I get, and tt get cancels, so the expression will be 1 by s minus 1 divided by s plus 1 by t. So this is like Laplace transformation of e to the power of at will be equal to 1 divided by s plus a, e to the power of minus at. So what we can do is, a is 1 by t, I will be taking e to the power of minus at, e to the power of minus small t divided by capital T. So the Laplace inverse of this will be e to the power of minus small t divided by capital T, where 1 by t is a constant. So this is the controlled output variable for unit step input. It will be 1 minus e of t minus t. After completing this, again there will be an error in transient response also. We need to fix what is the error in the system. What is the error? This is the equation of controlled output variable. Next I will take error. What is the error? Error is nothing but it is e of t. What is e of t? This is the error signal here, e of s. So directly I got an equation in C of t. Directly I will write what is the error in terms of t only. Error is nothing but reference input signal minus controlled output signal. Since it is having unity feedback, h of s is equal to 1. Whatever the output we obtain, that itself is the feedback signal for this type of system. What is R of t? R of t is 1 minus, what is C of t? C of t is this one, 1 minus e to the power of minus t by t. So if I multiply, I will get 1 with cancels, minus into minus plus, e to the power of minus t by t is the error signal for unit step input. Error signal for unit step input. So that means the error signal will be varying exponentially. That means this is the part what we get. So if I draw a plot, time versus controlled output variable, time versus controlled output variable, the error signal will be decreasing exponentially. So this is the error signal plot for this type of response. Then after getting this, if you give negative values, you will get this plot. And this is the maximum output what you can get. This is C of t. And if you make this 1 when t is equal to capital T, then E of t will be having 0.643 value. So that means exponential of 1, e to the power of 1 value you will get, and at this point somewhere you will get 0.6432, 64.32%. That means error signal will be 1 if the input is having 63.2% of input. That means error signal will be 1 if the input is having 63.2%. That is the graph for unit step input. And sometimes what we will do is even we can calculate the value of t also. When you got 0.632 is when t is equal to capital T. Apart from this, location of steady state error is very important. What is steady state error? Steady state error is nothing but limit of t tends to infinity E of t. So this is, in previous sessions what we were doing is we were writing error signal in terms of S. So there will be a conversion from t to S using final value theorem. Here directly we will write infinity. So ESS of infinity means the limit will be maximum infinity. What is steady state error? If you substitute this, if you put t is equal to infinity, so e to the power of infinity is how much? What is the e to the power of infinity? When you take up a Laplace transformation, e to the power of infinity is 0. So you will get the steady state error 0. That means for unit step input, steady state error does not exist for the first order system. So this is how we need to derive. We started with a basic block diagram of first order system. Then my intention is to calculate what is C of t. Here I will be calculating always what is C of t. This I need to calculate in time response analysis. What is C of t? First we want C of S. C of S we will get closed loop transfer function. If you use this closed loop transfer function formula, you will get C of S. Then R of S is the reference input signal. If you solve this, then you will get the equation in terms of C of S. If you apply Laplace transformation for this, because this is an improper fraction, we have to take the values of A and B with the help of method of partial fraction. If you use method of partial fraction here, you will get A and T. This is the equation what you will get. If you apply Laplace inverse for that, you will get equation in terms of C of t. After getting that, find out what is the error signal, then find out what is the steady state error. So this is steady state error. So why we need to calculate steady state error for transient response? Sometimes we need to adjust the value of amplitude. That means in the transient response initially the amplitude will be high. That high amplitude is required whenever to start a system it will be having high inertia forces. We need to overcome the high inertia forces because of we need high amplitude. After that we don't want that high amplitude because it is undesirable. I want to reduce the amplitude. How much I need to reduce the amplitude? For that again it is decided based on the error. After that the damping is provided in order to reduce the amplitude of the signal. Finally it maintains at the stable steady state response. Let us derive the second case, that is unit ramp input. So again this condition remains same. We need to obtain the closed loop transfer function. Why we need to obtain closed loop transfer function is to get C of t. So let us see what is unit ramp input. R of t will be equal to A into t. Since it is a unity, A equal to 1 because it is unity. So if A is equal to 1, R of t will be equal to just t. And what is R of s? R of s will be equal to Laplace transformation of t. So if you apply Laplace transformation here, Laplace of t to the power of n is n factorial divided by s to the power of n plus 1. N factorial divided by s to the power of n plus 1, provided if n is an integer. If n is a fraction, you will get gamma. So let us remember only that one. It will be 1 factorial divided by s to the power of 1 plus 1, that is s square. I will be using the same equation. Therefore, C of s will be equal to, what is R of s? 1 by s square into 1 plus st. Directly I will write method of partial fraction here only. It will be a divided by s square plus b by s plus c divided by 1 plus st. So 3 terms will be there in this equation. If I simplify this, what happens? Take the LCM. If I take LCM, LCM is denominator term common, s square into 1 plus st, that will be equal to, so multiply this s square into 1 plus st here. This is also having s square into 1 plus st. So a into 1 plus st, if you multiply this, s square will get cancels, plus bs into 1 plus st plus c s square. So this is what the equation you will get. These two terms will get cancels. 1 is equal to a into 1 plus st plus bs into 1 plus st plus c s square. Find out the values of a, b and c. First I will be using the known thing 1 plus st is equal to 0. I will put s is equal to minus 1 by t. Then I will get 1 is equal to a into 0 plus, again this term will also become 0, bs into 0 plus c into minus 1 by t whole square. So what happens? This is 0, 1 is equal to c divided by t square. So c will be equal to t square. This is the first value what I will get. Then put s is equal to 0. If you put s is equal to 0, 1 is equal to a. Again b terms and c terms will be 0. Therefore a is equal to 1. What is the next step? The next step is challenging somewhat because we don't have any other values. In that cases, we need to equate the coefficients of s square, s and constant. How to get? First I will simplify this expression. On simplifying, 1 will be equal to a, the value of a is 1, I will put the value of a 1 plus st plus multiply this bs plus b s square t plus cs square. First I will segregate s square terms. S square, there are two things, one is bt and c. So bt plus c plus, next is s term. If I take s common here, it will be b plus t, then a constant term is 1. Here it is 1. The meaning of this is there is no s term and there is no s square term. Now I will equate coefficients. So equating coefficients, you can equate any of the coefficient. I will be equating s to the power of 1 coefficient, then s to the power of 1 term is b plus t, but here it is, there is no s term here, so b plus t is equal to 0, b is equal to minus t. So you got the values of a, b and c. I will be substituting those values again here. C of s will be equal to, what is a? A is 1 by s square plus b is minus t by s plus c is t square divided by 1 plus st. So a, b, c values has been simplified. Then what I will do is, I will simplify this term by taking t as a common. So 1 by s square minus t by s plus, if I take t common here, it is s plus 1 by t. So 1t will get cancels. So 1 by s square minus t by s plus t divided by s plus 1 by t. So this is C of s. In the next step, what I can do is, I need to obtain C of t. What I will do is apply Laplace inverse. If I apply Laplace inverse, C of s changes to C of t will be equal to Laplace inverse of 1 by s square minus t is a constant, Laplace inverse of 1 by s, again here t is a common, Laplace inverse of 1 divided by s plus 1 by t. What is Laplace inverse of 1 by s square? It is just like Laplace inverse of t, 1 divided by s square. So this is small t minus, what is Laplace inverse of 1 by s? It is 1. So t into, directly you can write 1 into t is t plus t into, what is this Laplace inverse of 1 divided by s plus a? It is e to the power of minus a t. So e to the power of minus small t divided by capital T. So I will take t common again, t minus capital T into 1 minus e to the power of minus t by capital T. So this is the expression for controlled output variable for the first order system with unit ramp input. Let us see what is the error signal. Error signal E of t. E of t is given by R of t minus C of t. Why minus C of t is because it is having unity feedback system. What is R of t? R of t is t for unit ramp input. It is t minus this term, minus of t minus t into 1 minus e to the power of small t by capital T. If I multiply this t will get cancels, minus into minus it will be plus, it is t into 1 minus e to the power of small t by capital T. This is error signal. Then we need steady state error. What is steady state error? Steady state error is Es of infinity. So Es of infinity, this is just a limit. It is limit of t tends to c infinity E of t. What is limit of infinity is given by, again, limit of t tends to infinity. If you give t as infinity, so e to the power of infinity is 0. What 1 minus 0 is 1. 1 into 2 is t. So it will be t into limit of, I will write the step, t tends to infinity, 1 minus e to the power of infinity. This value will be 0. So the steady state error will be t. So let us write the graph in order to know what is the variation. So this is time and this is controlled output variable. Whenever we take ramp input, this is a characteristic of ramp input, R of t will be equal to t. Then according to this equation, C of t, t minus t into something. So it is increasing almost like a parabolically. This is a characteristic of this graph. If I find out the steady state error, this is a steady state error. This is how much we got. ESS will be equal to t. So this is the characteristic graph for first order system with unit ramp input. The next case is unit impulse input. So unit impulse input is nothing but, directly we can write R of s is equal to 1. It is a derivative of unit step input. So let us see how to obtain C of s by R of s for unit impulse input. So C of s is nothing but R of s divided by 1 plus st. So R of s is 1. So directly 1 divided by 1 plus st. So again, using partial fractions, only one terms, 1 plus st. So directly you can write what is the value of a. Where the value of a is 1. No need of simplification here. So if you apply L inverse directly, Laplace inverse will be equal to C of t will be equal to, again if you take s as a common here, so that means 1 divided by 1 plus st. So 1 divided by t into s plus 1 by t. It will be e to the power of minus t divided by, transformation of this is divided by t. So this is the controlled output signal. So if you consider the unit step input, if you take derivative of unit step input, you will get unit impulse input. This is a characteristic feature, and if you take graph, it is just like it is exponentially decreasing. This is a graph for unit step input, unit impulse input.